Hi all. Today's session is just for giving a briefing about the basic concepts of chapters which are there for the first term portion of CBSE exam in physics. Okay. So the first chapter, I'm just quickly surfing through those contents only. We'll have another session for discussing important questions as well. Okay, so straight away, let's move to the various contents of these chapters. You know that the first chapter we have is electrostatics. The chapter 1, that is static electricity, that is field and electric field and charges. You know that the very basic concept is we have the first equation to know is plus or minus any. The total charge possessed by a body can only be an integral multiple of charge of an electron. E is the fundamental charge, which is charge of an electron. So this is the concept, this is the equation we're getting from quantization of charge. Then we have the, once again let me tell you, we are talking only about the basic equations which are there in this chapter for you to just have a quick recap. Okay, so the questions we are not discussing in this session, remember that. Then we have the Coulomb's law concept. In Coulomb's law, we have the equation F is equal to K Q1 Q2 by R squared. You remember this equation is applicable only for point charges, where K is equal to 1 by 4 pi epsilon 0, whose value is 9 times 10 to the power 9. You know the unit is Newton meter squared, Coulomb raised to minus 2. The value of K. That is when there is a free space. Okay, if there is a medium, instead of epsilon 0, we will write epsilon. And you know that epsilon is what is termed as the permittivity of the medium. We have a term called relative permittivity, which is nothing but the ratio of the permittivity of the medium to that of the free space. Sometimes this epsilon r can also be represented by the letter K, capital K, which is also called dielectric constant. So relating the equation for the force when it is in free space or when it is in a medium, we have an equation to remember. Epsilon r, that is permittivity, is nothing but F0 by F. So that means force in a medium is always less than the force in free space. When the charges are kept in a medium, the force between them gets reduced by a factor equal to the dielectric constant of the medium, otherwise relative permittivity. So for example, relative permittivity, if it is 10, let's say if the relative permittivity of a medium is 10, then the force would become 1/10 of the original force. This is about Coulomb's law. From Coulomb's law, we are again getting an equation which is for electric field. Electric field is nothing but the force per unit positive charge. So we have the equation electric field E is equal to KQ by R squared. Be clear about this aspect. Coulomb's law and this equation for electric field intensity at a point, all these are applicable only for point charges. So KQ by R squared is the equation for the force acting per unit positive charge when kept at a distance R from a charge Q. Okay, that's about electric field. So if you know the value of electric field, force on a charge can be calculated by using the equation F is equal to QE. So whenever you are asked to calculate the force on a point charge when kept at a point where there is electric field strength of E, then we can say F is equal to QE. You know the unit of electric field is Newton per Coulomb. Unit of electric field is Newton per Coulomb, SI unit. Okay. Then we have the next point to think about is a dipole, electric dipole. Electric dipole is nothing but two equal opposite point charges separated by a finite small distance. This distance is usually represented by the letter 2a, distance between the two. And a quantity which is associated with this is what is called dipole moment, represented by the letter p, which is q times the length. So the unit of dipole moment is Coulomb meter. You know that dipole moment is a vector quantity whose direction is from negative to positive. Okay, this is the direction of the dipole moment. Dipole moment. Okay, equation for dipole moment is P is equal to Q into 2A. It's a vector quantity. Its unit is Coulomb meter. What else we have is the electric field due to a dipole. Electric field due to a dipole. Okay, there are two cases to think about. One, the electric dipole, if it is kept like this, okay, the value of electric field on the axial line over here. At this point, what's the value of electric field, which is maybe at a distance of r from the center of the dipole. The equation, dipole is of length 2a. The equation for the electric field at a point on the axial line of the dipole is EA is equal to 2 kpr divided by r squared minus a squared the whole squared. Memorize this equation. Value of electric field over here. Okay, it's always remember the electric field, the dipole moment is like this, from negative to positive. And also you should know that the electric field will be in this direction. Electric field along the axial line will always be along the direction of the dipole moment. Whereas you consider another point, which is the perpendicular bisector or equatorial line of the dipole. At this point, the value of electric field will be always anti-parallel to the dipole moment, that is opposite and parallel to dipole moment. The value of electric field at this point, which is the perpendicular bisector, is Kp by r squared plus a squared the whole raised to 3 by 2. So both the equations you should memorize. The expression for electric field at a point on the axial line and at a point on the perpendicular bisector. In both the cases, that if mentioned about short dipole, if it is a short electric dipole, then axial line equation would be, it would become 2 kp by r cubed, and on the perpendicular bisector the equation will be kp by r cubed. So which shows that the electric field at a point on the axial line will always be twice that at a point on the perpendicular bisector of the dipole. Okay, that's about electric field. So what all points is, that is electric force, the force between 2 point charges, that is Coulomb's law, then electric field intensity, the expression for that. Then we have electric dipole, the expression for electric field due to a dipole on the axial line and perpendicular bisector. Okay, moving on to the next. We have another term that is called torque experienced by a dipole in a uniform electric field. Remember, whenever a dipole is in a uniform electric field, if the dipole is kept at an angle like this, this is the way a dipole is kept at an angle theta, then it experiences no net force. Remember, as long as the field is uniform, the net force acting on the dipole will be 0. Whereas there is a torque, because there are two equal opposite forces acting, one force like this and the other force in this way. So these two equal opposite parallel forces will constitute a couple. The moment of couple is what's called torque, and the torque over here is calculated to be Pe sin theta. Memorize this equation. It's an expression for the torque acting on a dipole when it is kept at an angle theta with the electric field intensity of strength E. So which very well shows that if the dipole is placed parallel to the field, it becomes, torque becomes 0. If it is perpendicular, there is maximum torque. All those points you can make out. And half the maximum torque will be there if the angle theta is 30 degree, because sin 30 is half. Alright, that's about torque experienced by dipole. Another term we have is about electric flux, which is represented by phi. And phi, flux, is given by the equation phi is equal to Ea cos theta, where E is the strength of the electric field and A is the direction of the area vector, which is the vector which is normal to the surface. Okay, that's the direction of area vector. Maybe if the surface is like this, then the electric field is in this way, and if the surface is in this way, the area vector will be like this. So angle between the area vector and the electric field vector would be like this, theta. So we have an equation, electric flux phi is equal to Ea cos theta. So that way electric flux is measured by the unit Newton per Coulomb meter squared. This is the unit of electric flux. Basically, electric flux is a scalar quantity, because electric field is a vector quantity, area vector also, it's a vector quantity. So we can write the expression for phi in the vector form as E dot A, dot product. Whereas torque equation we will write as what? E cross A. It's a cross product. E cross A for electric, the torque on a dipole, and the electric flux is E dot A. Okay, we'll clear the screen. That's about electric flux, and total flux is calculated by using a law that is called Gauss's law or Gauss's theorem. Under Gauss's law, we have the basic idea about Gauss law is integral E ds. is net charge, or 1 by epsilon 0 times the net charge enclosed by a surface. See, remember, Gauss law is applicable for a closed surface. As long as a surface that encloses a given amount of charge, which is the net charge Q net, then the total integral integral EDS refers to total electric flux through the surface is given by the equation 1 by epsilon 0 into Q net. So memorize this equation, but this part is nothing but we can say total flux only. Total flux is 1 by epsilon 0 times net charge enclosed by it. Okay, based on Gauss's law, we have two derivations to learn, or two equations to learn to derive expression for the electric field due to a long charged wire. Suppose this is a charged wire, it's a long charged wire. Okay, the electric field at a point over here is found using Gauss law. There is an equation. This equation for electric field, you memorize it as E is equal to lambda by 2 pi epsilon 0 r. This is the expression for the electric field at a point due to a long charged wire. What is lambda here? Lambda is nothing but the linear charge density. Whatever be the length you consider, charge by length. That charge divided by that length. That is linear charge density of the wire. That's what you measure as well as a long charged wire is concerned. So this is one equation which we are getting from Gauss's law. And another equation is for electric field due to a charged sheet. Long charged means infinitely charged sheet, we say. A point close to it, if you take into account, very close to the sheet, if you consider its point, you should see that the equation for electric field at this point is nothing but E is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. You know where sigma is nothing but the charge density, surface charge density, means charge per unit area. This one is linear charge density, charge per unit length. This is surface charge density, charge per unit area. So one thing obviously you can make out, the first equation depends on R. How much is the electric field at a point due to a linear charged wire? That depends on the distance R. It is inversely related. Whereas in second case, infinitely charged sheet thing, the electric field doesn't depend on the distance. You know, there is nothing, no R here. That means in the first case, the graph between electric field and the distance, you can draw like this. You know, it is inversely proportional. Whereas the other one, it is independent electric field due to a sheet of plate. Okay, a sheet of charge. Okay, sheet of charge is independent of the distance r. Clear? That's about Gauss law and application. These two are the two applications you have to learn. That's it from the first chapter. Now we move on to the chapter 2. Chapter 2, basic idea we have to have is about potential. Okay, potential V is nothing but how much is the work done per unit positive charge. So this is actually, if you compare with what you studied in the previous chapter, there we have studied electric field is force per unit positive charge. Here electric potential is work done per unit positive charge. That is what why the unit of this is joules per coulomb, but joules per coulomb is what is referred to as volt. Okay, then we have a term called potential difference. That potential difference is like generally work done to bring a unit positive charge from one point to the other is what is potential difference. Generally we can say. How about potential? It is work done to bring a unit positive charge from infinity to the given point. That is potential. Potential differences between any two points. And based on that we have an equation. If V is the potential difference between 2 points, then the energy it gains, the charge gains is W is equal to QV. So if Q charge is placed under a potential difference V, it gains energy of QV. Otherwise, there is a work done by the field on the charge QV. So energy gained is QV. But you know, if you release that charge particle in the field, that will go as a kinetic energy. So generally we say this kinetic energy half mv squared is equal to QV. Memorize this equation, important equation. It shows that how much kinetic energy a charged particle will gain when it is accelerated under a potential difference V. If it is electron, instead we will say EV is equal to half mv squared instead of QV, right? E. You know that E is charge of electron. So under 1 volt, how much kinetic energy it will gain? Therefore, 1.6 times 10 to the power of minus 19 coulomb joules of energy it will gain if one electron is released under 1 volt potential difference. That energy is what is referred to as electron volt. So electron volt is the energy gained by an electron under a potential difference of 1 volt, which is calculated to be 1.6 times 10 to the power minus 19 joules. Okay, memorize this value as well. So potential difference. Now we have another term, that is potential energy. Potential energy, whenever the two charged particles, are kept separated by distance. See, Q1 and Q2, two charges are kept separated by distance. So these two, because of the interaction with each other, they possess some energy. That energy is nothing but in the form of potential energy, and it is calculated using the equation K Q1 Q2 by R. K Q1 Q2 by R is the expression for potential energy between 2 point charges. Suppose if there is one more charge coming, maybe Q3, one more charge is there. So there are 3 pairs of charges, Q1, Q2, Q3, 3 pairs of charges. So the distance between each pair of charges we have to take into account. In one pair, how much is the distance between the 2 point charges? That should be taken into account. So in that way, we calculate the potential energy between Q1 and Q2, Q2 and Q3, and Q1 and Q3. Then add all the potential energies together will be the potential energy of the system. Okay. Now, let me summarize this point to make it clear. We know the equation for the force between 2 point charges is Kq1 Q2 by R square, which we studied in the first chapter. And here the corresponding equation is potential energy is Kq1 Q2 by R. Just learn the comparisons. So don't get confused with potential and field. Potential energy, electrostatic force. Okay, they are similar quantities. Means the equations look alike. Then we have equation for electric field, F by Q0, force per unit positive charge, whereas here we have potential W by Q0, means work done per unit positive charge. Electric field equation, KQ by R squared. Similarly, equation for potential due to point charge is KQ by R. We know that force on a positive charge or force on a point charge in an electric field is F is equal to QE. Like that, we have the equation here, W is equal to QV. That is the energy gained under a potential difference. Next, we have a small equation that relates the electric field and potential. So, relation between field and potential. Relation between field and potential is E is equal to minus dV by dx. Okay, to be read as electric field is the negative gradient of potential with distance. Negative gradient of potential with distance. That is the relation between electric field and potential. And also from this we are getting the magnitude of electric field when there is a potential difference V between 2 points where separated by distance D is E is equal to V by D. This is the equation which normally we use in capacitors and all. Okay, and the point to be clear about is the electric field is what is it? The line integral of electric field EDL is nothing but the work done to move a charge between 2 point charges. That is, you may clearly understand that potential difference can also be calculated as E dot dl. There's a point, potential difference E dot dl. You know, you may just compare with what you studied in the 11th standard. Work done is equal to F dot dl, no, or dx. Force and distance. Like that, electric field is nothing but force per unit positive charge. Okay, E dot dl. So memorize this equation for potential difference. Also, it may be some useful concepts for some numericals and all. Okay, there's a relation between potential difference and electric field. The next, let me clear the screen. The next what we have is about capacitors. Okay, the capacitors I mentioned at the beginning. I'm just mentioning only about the basic equations which are useful for numerical problems and application level questions. So the capacitors, the very basic equation is, you know, in a parallel plate capacitor, the capacitance can be calculated using the equation C is equal to Q by V, charge per potential difference, and the unit of capacitance is farad. The capacitance of a parallel plate capacitor you can calculate using the equation epsilon 0 A by D. Here A is the area of the plates and D is the distance between the plates, A, D. Okay, that's the case when there is free space or air between the two plates of the capacitor. Then we have another concept is capacitance of a spherical capacitor will be 4 pi. Memorize this equation also, 4 pi epsilon 0 R. So the capacitance of spherical capacitor is directly proportional to the radius, and capacitance of a parallel plate capacitor is directly proportional to the area of the plates. Also, we have an equation C by C0 is epsilon r, or it's also represented as K, which is called dielectric constant. Or we can rewrite this equation as C is equal to K C0. Whenever the dielectric medium is used, whenever the capacitor is filled completely with a dielectric of dielectric constant K, then the equation for the capacitance becomes K times the original capacitance. Okay, and when capacitors are connected in series like this, even three capacitors are connected in series, remember, don't get confused with the equations. 1 by C1 plus 1 by C2 plus 1 by C3. This is how we calculate the effective capacitance. So remember, whenever we have capacitors connected in series, the effective capacitance CS can be calculated using 1 by C1 plus 1 by C2 plus 1 by C3. 1 by CS is equal to 1 by CS is equal to. So don't say that CS is equal to, because that's one of the common mistakes many of you make. So this is in series combination, and in parallel combination, the capacitance can be calculated using C1 plus C2 plus C3 directly. Just add them up. That will be the capacitance. So always remember, in a series combination, the effective capacitance will always be reduced. In series combination of capacitors, effective capacitance will always be reduced. But this reduction happens because you know that as you connect the many capacitors in series, it can be treated as one single capacitor with a large distance between the plates. More distance means capacitance will be reduced. Whereas in the parallel plate capacitor parallel combination of the capacitors, what we get to know is when they are connected together like that, the effective area between the plates is getting increased. That's why the effective capacitance will also be more. You know that capacitance is directly proportional to the area of the plates. So that's one thing about that. Is I said about what is the basic idea about capacitance. When dielectric medium is kept, two types of capacitors, parallel plate capacitor and spherical capacitors, and two types of combination of capacitors, series combination and parallel combination. And we have two more equations to think of. One is when a capacitor is there with a conducting slab between them. Conducting slab is kept between the plates of the capacitor. Say this is a capacitor and there is a conducting slab of thickness T is kept between the plates of capacitor. D is the distance between the plates. Then the capacitance is calculated using the equation C0, which is the original capacitance when there is no dielectric slab. Sorry, no conducting slab. This is a conducting slab. 1 minus T by D. So memorize this equation. This is the capacitance of a capacitor when there is a conducting slab of thickness T kept between the plates. Whereas if there is a dielectric slab, in a dielectric slab, the capacitance can be calculated using the equation C0 by 1 minus T by D into 1 minus 1 by K, where K is the dielectric constant of the slab. Okay, actually from this only we can even get to know about the other equation. C is equal to K C0 by keeping small t as equal to D, means the entire space is filled with dielectric constant K. So from the first two chapters, these are the fundamental equations. That is the first two chapters in the sense electrostatics. Okay, first chapter mostly deals with the vector quantities, and second chapter is mostly dealing with the scalar quantities. In fact, one more equation I was to mention about at this point of time, that is nothing but how much work is required to turn a dipole in a uniform electric field. That's nothing but PE into cos theta 1 minus cos theta 2. This is the equation which you would use to calculate how much work is required to turn a dipole from an angle theta 1 to an angle theta 2 in a uniform electric field. W is equal to P into cos theta 1 minus cos theta 2. And based on this equation, we can even get an expression for the potential energy when a dipole is placed in a uniform electric field at an angle theta. The potential energy can be calculated as minus Pe cos theta. This is the expression for the potential energy of an electric dipole when kept in a uniform electric field at an angle theta. Is it clear? So there may be question like calculate work done to turn a dipole from stable equilibrium to unstable equilibrium. Remember, when theta is equal to 0, it is considered to be a stable equilibrium, and theta is 180 degree, then it is considered to be an unstable equilibrium. Unstable equilibrium is the case when the potential energy is maximum, positive. Okay, if it is negative potential energy, it is considered to be stable equilibrium. All right, so that's about potential energy. And in vector form, this potential energy equation can be written as U is equal to minus P dot E. It's a dot product. You know, the dipole moment P and the electric field E, both are vector quantities, whereas the potential energy is a scalar quantity. I hope it is clear. The first two chapters. Remember, I have already explained the concepts of electromagnetic induction and AC basic concepts. That is there in another video. But this one is only for the first two chapters. The next one we will have about the chapter current electricity. Okay, so we will have it in the next video. Thank you. Hope you'll be preparing well for the coming examination, and this is the first term portions are only limited. That's why we're talking in terms of the small brief concepts. If you're okay with concepts, then the things will be clear. Okay, see you with another video for the next chapter, current electricity. Okay.